ready to start with our new section. And like I said at the end of the last section, we're going to take some ideas of this probability distribution curve and make them a little more formal. So as you recall, last time we had superimposed a graph over this, and that graph had behaved in what was perhaps able to be described in a normal fashion. And at the time we had said that Chebyshev's theorem, which is designed for any distribution of data once we have sigma and mu, was able to guarantee us some formulas. So recall Chebyshev's, which I shall abbreviate, said that our formula was going to be 1 minus 1 over k squared, and this would be the minimum chance for k bigger than 1, k number of sigmas. And I've abbreviated this deeply, but Chebyshev said that if you let the number of standard deviations that you travel on either side of average be bigger than 1, then 1 minus 1 over k squared will give you a minimum probability. And this works for any collection of data. And so last time I had mentioned that the expected value of a 17 student class was going to be 9 students plus or minus 2. And the graph we had drawn was looking something with little dots like this. The difference being, of course, that those dots were discrete. There was a specific dot for each student, and we had head counts. Now we're going to talk about a continuous distribution, things where there's so much information that we don't have dots, instead we have a solid line. First of all, let's get some things to think about. We're trying to calculate the total probability, and if you'd looked at the dots that we had drawn last time, you'd see that if we added up all the probabilities of each dot, we would expect them to sum to 1. So when we connect the dots with a smooth curve, like I've done here, we expect the total probability to add up to 1, and since the height is the probability of a particular value, what we mean is that the area under the curve, if I could shade this all in, should equal 1. So we have this idea that area under curve equals 1. And that's pretty cool. Another idea we have is that because this is a continuous probability distribution, just as we saw last time, the probability of 0 students not earning an ABC in a class of 17 was 0.00000026, very small, but still something. No matter how far to the left or right you go on a continuous data variable scale, we have this sense that there's always a slight probability that it could happen, which means this line might get closer and closer to our x-axis, but it's never going to quite touch. Line never touches. And what that means is that there's always a slight possibility that any particular value could be achieved. Is it likely? No. But could it happen? Maybe. We put in the middle the most common things, and just as we saw with that chart, the most likely average, the mean, mu, is going to be right dead in the center. And now is the time when we're going to move ourselves a little bit away from the realm of any probability distribution or any type of curve and talk specifically about normal ones. Now remember, way back in the first module or second module that we talked about, we were definitely in the business of looking at shapes of histograms, and we said some were bimodal and some were mound-shaped, which we also called normal, some were skewed. This is a normal distribution, and its feature is that it starts out low, gets high, and comes back down again. And when we have a normal distribution, we can do ourselves a lot better than Chebyshev's theorem, because Chebyshev talks about minimums. And that includes very twisted skew shapes where we can't guarantee that our data is behaving normally. But when it does behave normally, we're actually able to get ourselves something a little bit stronger. So first of all, let me say a little more explicitly then well, the histogram should build itself up and build itself down, what I mean by normal. In particular, properties of a normal curve include the fact that our curve has a total area under the curve of 1. The line never quite touches. That's important. We have symmetry. So it's not skewed in one direction or the other. It's perfectly balanced on either side. That's nice. We also expect our curve to be what we call bell-shaped. It's not enough that there's symmetry, but this idea that it clusters in the middle and it tapers off as we go off to the sides. That's the idea of bell shape. And finally, notice that this part of the curve is what we call concave down. And this might sound a little bit like calculus, but bear with me for a second. It's concave down, meaning I'm cupping my hand and the cup part is pointing down. Whereas over here, my curve is concave up. If I held my hand and faced in this shape, I could pour water into my hand and I'd be able to hold it. So concavity, just like think convex or concave lenses, concavity is the part that could hold water. Here the bowl part's pointing down, here the bowl's pointing up. It changes then from curving down to curving up, and that happens right about here. This is called an inflection point. If you talk about graphs. And it is a feature of a normal curve that the inflection point occurs at sigma plus or minus mu. So one standard deviation to the right and one standard deviation to the left is where we have that inflection point, where it stops being concave down and starts being concave up. These are features of normal. And we'll talk about the Pearson skew index a little bit later to discuss how to sort of confirm that data is normal. But for the moment, if we've got a graph, this is what normal means. It's bell-shaped, the curve never quite touches, and we've got symmetry, and we have a concavity change at one standard deviation away. And if we have this scenario, then much more powerfully than Chebyshev's theorem, we have in fact what we call the empirical rule. So let me draw that up. And I think that starts with an E there, but we then have I. And the empirical rule says this. We're going to go and travel in standard deviations, just like Chebyshev suggests we do. Sigma plus mu plus sigma 2, and mu plus 3 sigma. And I'm not very good at drawing, so pretend like these are all the same spaces. Mu minus 2 sigma and mu minus 3 sigma. If you've ever studied business policy, you will probably see the phrase 6 sigma thrown around. And 6 sigma simply means 1, 2, 3, 4, 5, 6. So obviously at 6 sigma, my curve would be very close to touching my x-axis, and that would mean the chances of something happening at 6 sigma are very, very small. It's a little finer measure of control. For most intro probability courses, we tend to stop at 3 sigma because, as we're about to see with the empirical rule, even once you reach 3 sigma, you start to have very small odds. Because here's how the world works in the empirical world. I'm going to draw in blue lines here, these vertical ones, little areas. And each one of these areas, I'm going to label the chance of falling into them. Chebyshev says if we go 2 standard deviations in any direction, maybe I should draw this in a different color and format. So let's draw this series of dashed lines down here. Chebyshev says if we go 2 standard deviations in any direction, we'll get 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 3/4, which is 75%. But that's a minimum. It guarantees at least that, no matter how skewed my data might be. The empirical rule is a little bit more powerful, and it guarantees me this. 34% here. Oops. 34% here. Remember, it's symmetrical. So in this region right here, it's guaranteeing me 68%. In the 2 columns over here, we have 13.5%. And between 2 and 3 standard deviations away, we have ourselves 2.35%. Which means, if I add up this half, I'll have 13.5 plus 34. That gives me 47% on this side. Remember, it's symmetrical, so this area should be the exact same as this, so I can multiply that by 2. That times 2 gives me 95%. The empirical rule promises me that it's not at least 75%. It tells me it's precisely 95%. Since I expect, based on the curve of the binomial probability distribution of students in a class, and that curve looks very much like this one, since that curve was very close to being normal, I said there's a 75% chance that between 5 and 13 students would earn an ABC rate in the course, but that was at least 75%. In fact, I would be expecting that that would probably be closer to 95%. So the empirical rule is a little more powerful than Chebyshev, and it's allowed to be because it has a few more conditions. Chebyshev works on any sort of data, whereas the empirical rule is explicitly reserved for normal data only. However, a lot of things are normal, and so we can discuss problems that deal with normalcy. In fact, this introductory statistics course is called normal statistics for the most part. We will tend to, in most of our word problems from here on out, describe that everything's normal, and we'll say that explicitly, but the fact remains that even if we're not saying it, odds are we're discussing normal data. So what's normal? In general, if you take a good random sample of anything that is remotely biologically based, it will probably be normal. If I measure people's heights, well, they'll have a certain maximum height and a certain minimum height. If I measure people's weights, if I measure blood pressure, if I measure anything on any of our ratio level data, remember we had nominal, and then we had cardinal, and then we had interval, and then finally we had ratio where it had true zero. If you measure anything that fits on those types of scales, that is a ratio level data, and it has some sort of connection to biology, you start to expect it to be normal. Oftentimes, things that are also normal are anything that has to do with people. Again, not entirely, but if it's a random, across-the-board collection of data, you would expect it to be normal. On the other hand, what's not normal? Well, what if I decided to run an ethics test, and I asked questions about how ethical you behaved, and you could rank it on a scale from, let's say, 1 to 5, and there was lots and lots and lots of questions I asked, enough that we could model it with a continuous curve. It would be normal if I asked these questions to a random sample of everyone in America. America may be more or less ethical than other countries, but we inside of this country would behave normally. Excuse me, I really should say United States, America, perhaps. However, if I instead of grabbing everyone, grabbed two populations, one, my grandmother's bingo group, and the other, people at a maximum detention prison facility, I might expect that data to not be normal. They're very different groups of people. I might expect it to cluster mound shape and be kind of the opposite of this, very high on either of the edges for ethical or unethical behavior, and then swooping into the middle. And I'll leave you to imagine whether the prisoners or my grandmother's bingo troop are more or less ethical. I can tell you, though, that bingo gets pretty fierce. So, as we're looking at this empirical rule, we are expecting to talk about normal things, and all of our rules about random samples and standard deviations obviously come into play here. Some convenient things to notice about this, some things to think about. The area under the curve adds up to 1. And if you truly want to understand statistics and really get a good sense for why all of this is working, then you're going to have to take calculus, because calculus is the part of math that deals with areas under curves. And we have those formulas that can show us that this area is a total of 1, even though this curve goes on forever in both directions. And as a side note, that's a very fascinating thing. This is an infinitely long line. It goes off forever here and here. However, I can still promise you that the area under it is 1, a very limited, finite number. That's rather strange, but it's one of the powerful tools that calculus provides. And anytime you start dealing with very advanced statistics, all the classes after this one, you'll start to eventually see calculus as a useful prerequisite. But for right now, we're still talking about intro statistics, and we now have our empirical rule that tells us if it's normal, we can do a lot better than Chebyshev. Forget at least 75, let's try 95% in between two standard deviations in either direction. Once we have a sense of these standard deviations being a certain level of very common or very not common, we can start to say some other things. What does it mean that 95% lives in the middle? Well, it tells us that only 5% lives on the outsides. So if I was to try to shade in all this area, I would have 2.5% over here on this side. And I would have 2.5% over here on this side. And I draw those arrows to show again that it's going on forever in either direction. And so there's 95% in the middle in between two standard deviations, and only 5% of the time would I expect it to normally fall outside. So let's say, so I try to find my marker. Let's say that I have a little person who's standing out here. One of my actual people really honestly fell outside this range, whatever this range might be for whatever we're studying. Maybe we're discussing height, and this person is actually quite tall. Shaquille O'Neal tall, maybe. In the case of that, we have to ask ourselves, did we expect this to happen? And the answer is, well, not really. But is it happening in a strange way? And if it's just one person, the answer is probably no. We expect some people to fall far to the right. Not a lot, but we do expect 2.5% of everyone to fall somewhere more than 2 standard deviations away. Contrary-wise, we expect 2.5% to fall less than 2 standard deviations away on the left side. We expect it to go off that way. You have this idea then that as long as you're talking about one single person, maybe you can expect some interesting things to happen. However, let's add a little bit more into the mix. Remember, 95% in the middle, that leaves 5% for both ends. It's symmetric, so we snap that 5% in half and put 2.5% over here and the other 2.5 over here. But remember, I shaded it over, but we promised that there was 2.35 in between 2 and 3 deviations. So in particular, if someone's standing to the right of 3, what I really have is 2.5% minus 2.35%. Leaving with me with 1.15, percent. 0.15%. How likely is it to find someone this tall? Very unlikely in a normal population. So what does that mean? Well, if I walk into my classroom and I see that all my students are, let's say, 8 feet tall, I would say to myself, this is very unlikely. In general, if I had a randomly selected classroom, I would not expect my students to be 8 feet tall. There's only a 0.15% chance that that should happen for one person, and all of them are doing that. So I'd start to say to myself, this is a strange class. And then I'd look and say, oh, maybe I'm teaching statistics for basketball majors. You can gain a sense for what you expect based on probability, and it's not a problem if things aren't behaving the usual way. But you do have to ask yourself, is there a reason for it when it occurs? So let's take that and talk about the concept of control charts. Very near and dear to the heart of most business personnel. What you want to do is you want to make sure that you're not making a wrong decision. So let's keep this idea of an empirical rule in mind, but let's turn this all on its side. A control chart looks like this. Instead of drawing the normal curve, you just want to be able to grab some quick data points and plot them, and it works like this. You draw a horizontal line and you call that line mu. That's the normal level that you normally expect. Then you go one standard deviation away and you say, well, we expected that. Within 2 standard deviations on either side, we had 95% of everyone. So you don't draw anything here, but you do draw something 2 standard deviations away. You draw a dotted line, and you call this mu plus 2 sigma. Now this is a 3 sigma control chart. I mentioned in industry 6 sigma seems to be more common, but let's talk about this 3 sigma chart. Then, 1 standard deviation above 2 sigma is of course 3 sigma, mu plus 3 sigma. And I draw this line. I repeat the process on the other side. And again, I'm drawing this very roughly. Mu minus 2 sigma, and then minus 3 sigma. Now, with this control chart, we can actually compare some things and see what happens. On the right side, I've written the general descriptors. Let's go ahead and on the left side, write some actual numbers. And let's go back to that example where I had 17 students in a class. Sigma was 2, and mu was 9. So I have 9 here. That was the average number of students I'd expect to earn a passing grade. 2 pieces up is 2, 9, 10, 11, 12, 13. 1 more up is 15. 2 down is going to be 9 minus 4, which left me with 5. This was that 5 to 13 range we discussed. 2 fewer, 5 minus the sigma, for me to have a mu minus 3 sigma, is going to give me 5, 4, 3. Now let's talk about some different scenarios. In fact, let's talk about 3. What we're going to do is we're going to do a measure of what we call signals. And signals, which is this idea of either we're in control or out of control, is this. If I have my classes behaving according to this process and they're staying very close to mu, then I would say, that's okay. I expected that to happen. It has nothing to do with whether 0.53 on an absolute level is the right number of students to earn passing grades in the course or not. Keep in mind, I personally don't have any control over whether students earn passing grades in the class. That's up to them. However, I can identify if something different is happening in the class, and then maybe I can take steps to do something about that. How do I know if something different than normal is happening? What is normal? Well, that's what the control chart is going to tell me. There are 3 different types of what we call out-of-control signals that we look for. So let's say I take a peek at my last few classes. If I ever have a class that's above 3 sigma, let's say I get to the end of the class and I find that 16 out of the 17 students are about to earn an A, B, or a C. I would have to stop myself and say, that's not very normal. We'd call it out of control. Out of control could be a good thing. It looks like 16 students are about to pass. Probably before I went and awarded those letter grades, I would have to go back into my grade book and look and see, have I crazily done some weird typing? It would tell me, you better do an error check real fast. Did this really happen? I might take a look at the final exam and ask myself, how did everyone score this high? And then maybe I could find answers. And again, it could happen in many ways. Maybe this semester, a whole bunch of calculus students decided to come into statistics. If I don't change my teaching style and didn't, it's very unlikely that it has anything to do with me. However, if I've given the same final exam 5 years in a row, maybe it's because finally those final exams are leaked out. In fact, as a separate conversation about test ethics, you might be interested to read about some recent cases in academia where students have managed to acquire tests before they were given. I think the most famous one happened in Florida most recently. And the professor was able to detect that something strange had happened by using a control chart. And then furthermore, was able to statistically determine which students were engaged in this cheating process. But this doesn't have to be with students. You can use it with machinery, whatever. So if you're above 3 standard deviations Or if you're below 3 standard deviations, if only 2 people pass the class, or 1 or 0, we would say the system's out of control, and I would say something odd is happening. We better investigate further. What's the probability say? Well, remember, there is a 0.15% chance that this happened. There is a 0.15% chance this one happened. So is it impossible? No. Is it likely? No. And so here's what you want to detect. This is probably very rare, but it could happen. Again, there's almost 0.1%, a little over 0.1% chance that it did. So if you look carefully and calculate the probabilities of this, you find out that you don't care about whether this is an odd event. What you care about is it an odd event but legit, or is it an odd event and not legit? So you start to care about this idea that we will develop further when we start talking about confidence intervals, but you start to care about the idea that this is different than usual, but is it different and okay, or is it different and not okay? Let's put it this way. Think if you had a grid. And you had guilty and not guilty. Anytime you have a person go in front of a jury, the jury can vote that person as guilty or not guilty. So this is the jury. Now this person who's guilty or not guilty, in real life, they could either be a criminal or they could be innocent. If they were actually in real life a criminal and the jury voted them guilty, this is a good thing for society. We've correctly identified the guilty person and now we can determine a punishment. If the person's innocent and did not commit the crime and the jury says not guilty, this is also a good thing for society. We have correctly said, no, actually you did not commit the crime and therefore you don't deserve punishment. What worries us, of course, are these two corners. This is a very sad thing because we put an innocent person under some sort of punishment. And this is also a sad thing for the rest of us because there's now a criminal out there who's entirely heartlessly capable of slashing tires, maybe, who's out there ready to slash more tires. Our goal then, anytime we have some sort of decision process to make, is we would ideally like to make sure that we're living in one of these areas. So too with the control chart. Just because something's strange doesn't mean that it's the wrong call for it to be strange. Maybe it just happened. Or maybe it's strange and something very weird did happen. So what we care about is if I make the decision, when I look at the class and say, you know what, nope, this is too different. It's out of control. I have to figure out something. I'm getting ready to put my time into double-checking whether I've correctly calculated grades, into figuring out how students manage to get there. And so what I need to worry about is if I do all that work and then eventually say, no, it's legit. Nobody cheated. Everyone just worked really, really, really hard. They did their homework, they watched all these videos, and they followed all my steps and advice, and everything went great. Celebrate. You shouldn't have done all that work. You should have just put on your party hat. What I care about then is what we call a false positive. A false positive is when I decide that it's time to do something, and in fact, everything was working as it was supposed to. This just happened. So, we talk about how likely false positives are. And if you look carefully, the false positive for an out-of-control process where we use the 3 sigma calculation is going to be 0.003. That's how likely it is that this is a false positive. What do I mean by that? If I have a class where 16 out of the 17 students earn an ABC rate in statistics, I'm going to decide, since that's over 3 standard deviations, that that system is out of control, and I'm going to investigate. There's only a 0.3% chance that I'm going to find that this just happened. Instead, there is a, 99.7% chance that I'm going to find out something weird is going on, something abnormal, something different. Now, what that different thing is could be all sorts of things. I may find that what happened that was different was that all of these students had already taken calculus. And I hold up calculus as if this is some magic thing and every calculus student always passes stats. That's not true. What I'm saying is these students have practiced statistics and mathematics so often that of course they're going to do well in this class. They already have done that. Or I will find that I just created a whole new series of videos and it took me 48 hours to do that, plus editing time, plus uploading time and analysis time, and all of that effort has just paid off. It doesn't mean that all the students cheated their way through, though that's a possibility. What it means is I'm 99.7% certain that something significantly different happened at this time than what happened before, and it's probably time to revise those numbers of 0.53 and 0.47 for pass and not pass rates. Same thing down here. If only 2 students pass the course the way it's set up, it's time for me to say, you know what, it's out of control, and there's only a 0.3% chance that I'm going to incorrectly label that as something strange instead of me just so happen to get a whole bunch of students who are going to have not ABC rate as their final grade come into the course. 0.003 is very small. I'm happy with that. It's very unlikely that I'm going to go through the work of trying to figure out what's happening and accidentally make the wrong call that said I shouldn't study this further. Because if all the students are doing well, I want to find out what happened so we can repeat it. If all the students are doing not well, I want to find out what happened so we don't repeat it. And that work is going to pay off. There's only a 0.3% chance, that it's not going to. What are some other ways that systems can get out of control? Well, you don't always have something that falls above 3 sigma, so there's some other ways this can happen. It's possible that instead we get a trend. So anytime we have, and that one I think this is often called, these are called control signals, and I'm just looking at a little chart in our textbook. We also talk about, I'm just making sure that I'm writing these in the right order. It doesn't matter where they fall exactly. The point is nobody's falling necessarily above 3 standard deviations. If I have 9 that fall higher than average, so let's say I teach 9 classes. If my next 9 statistics classes that I teach all have more than, well, let me rephrase that. If my next 9 classes with 17 people in them all have more than 9 students passing, maybe this one had 10 students, this one had 11, this one had 12, this was back at 11, this one was 11, this one was 11, this was 10 again, this was 12, this was 12, maybe I guess that's 11, and this one's 10. These all had 17 people in them, and I count and I say, you know what, they're all falling above what I was expecting average to be. Then something different is happening. It's time for me to look and see, why did that occur? Because once again, everybody's falling above average. If everyone's above average, that means my average wasn't very good. Because remember, average is adding everyone together and calculating the usual. This guy's average should fall somewhere right here, and so this average here is higher than what we were actually expecting, so something's different. Again, it's time for me to say, maybe this just happened. You can have a run of good luck. All the students who signed up for these courses, they just so happened to be ready to go, and they didn't have any of the usual things that cause withdrawals or something to happen, or quits. On the other hand, of course, we could have the scenario that says something's changed. If I see this happen, which I think is probably much more likely than this, after creating these videos, I will give myself a pat on the back and say, good work. You made videos, this was very helpful to students, and that means you should keep the videos and also go back and recalculate what you expect to happen, because it's time to put the bar higher. And that's where that phrase comes from, incidentally. When you say it's time to raise the bar, what you mean is we've improved our process, and it's time to literally raise the bar. There's a new normal that exists now. Same thing over here. If I notice that all my students in a class are falling below average. And if I get at least 9 in a row, that's key, it's not just some, at least 9 in a row fall on the bottom side of the bar, then I know that I'm having fewer students pass than is normal, and this system, is also out of control. And it's time to figure out why. In fact, this did happen to me. Not in this state, not at my current school, but it did happen to me once, and we found out something. In fact, it wasn't even with students. But if you look at this, you can often find out that something's going on secretly that's changed the world in which you work. This actually happened with something in industry. There was a product that was being manufactured and it wasn't conforming to the testing norms. And what we found out is that one of the manufacturers who supplied the company had changed their process. They made a change that they thought was for the better, but when it was put into this other product, there was some overlap and some static between the communication signals. And I, as you can tell, don't know very much about the process because I didn't need to. I'm the statistical consultant, and I could say, what used to happen isn't happening anymore. This is causing you trouble. It's time to investigate. Investigations cause time delays because you have to shut the factory down and analyze some of the stuff. But we did investigate, and they told me that they eventually found the problem. We were able to fix it. If this happened with my students, I would start to ask myself, why? What's changed? Has my process changed? If my class hasn't changed, then I start to wonder, why are my students doing not as well as I'm used to expecting them to? And then I might look and say, I know what's happened. We decided to reorganize the textbooks, and maybe this lecture that used to happen in the previous class isn't happening anymore. Let's see if we can add it back in. So you can always have things like this, and you can decide, well, this guy's out of control. So out of control signal 1, somebody 3 deviations in either direction, you just need 1. Out of control signal 2, 9 on one side or the other in a row of your average mean. Next, what if we wanted to have a third signal? You could have all sorts of signals, but we only talk about 3. What we're going to have is at least 3 on one side, in particular, at least 2 standard deviations. So remember, this would be out of control. This, by itself, would not be out of control. But this would. This would also be out of control. Anytime you've got 3 in a row that are both on the same side of mu, and at least 2 of those are above 2 standard deviations, you're out of control. You don't need 2 in a row that are out of control. You just need, out of any 3 that you look at least 2 of them are above. So this, not out of control. This, not out of control. This, out of control, in the low way. Too many of them were in this 2 standard deviations, which, remember, 2 standard deviations in terms of the normal curve and the empirical rule puts you at only a 2% probability. So you start chaining those up together in a row, and you start saying this is unlikely to have happened for random reasons. Instead, there has to be some deeper purpose. So, our 3 out of control signals now are, you can have somebody 3 standard deviations away and you just need 1. That's so odd, it just takes 1. If you're inside of 2 standard deviations, you got to get 9 in a row on one side of mu before that becomes odd. And if you're going to be 2 standard deviations away, you need not just 2 in a row, that would work, but you don't need it. You can have any 3, you've got at least 2 on one side of 2 sigma, or at the bottom side, of course. So, and again, there's some different percents for those. I think that for the out of control signal 3 with 2 on either side, there's a 0.002 chance that you'll get a false positive. We said for the 3 sigma 1 there was a 0.003. It becomes very unlikely that you get false positives out of these. And that's why we pick these as our out of control signals. If I just picked If I just pick 6 on one side in a row instead of 9, it wouldn't be as likely that we'd have this happen accidentally. It would be a more normal thing that we would expect. So that's why we don't call him out of control. So we pick deliberately our out of control things to be stuff that is very unlikely to give us a false positive. I think I'm just about ready to be done, so let's try to set ourselves up for success in this current section. We're talking about normal distributions. The last section we talked about a probability distribution, then we talked about the binomial distribution, and now we're talking about normal distributions. Normal distributions are very much in the business of comparing a couple specific cases to the group as a whole. And when you do that, because it's normal, we're able to go beyond Chebyshev's percents, which are minimums, and instead have the empirical rule, which are much more inflexible. And we're able to do that because we've got our inflection points at plus or minus 1 sigma. We've got ourselves a bell-shaped symmetric curve. It's got an area totaling of 1, and so everything works out rather nicely. Our goal in this section is to be able to answer several questions. One of the questions we'd like to answer is, how tall am I, and how do I compare to everyone else? Other questions that we like to answer are things like this. If I have a particular class, and I know that 15 of my students are succeeding, and there's 20 students in the class, should I have expected that, or is that different and weird? Sometimes different and weird is good. Like I said, I'm recording these videos right now. I really, truly hope that I'm going to get to raise the bar with these videos and say, you know what, there's now a new level of success that my students get because my online students have a lot more support, and my face-to-face students can now watch these lectures whenever they want to. I hope that works. And so I hope that we do have an out-of-control signal soon. That would be wonderful. Other times, if you talk about factory production, or if you talk about success of flu viruses, maybe flu virus inoculations, you hope that you can get these out-of-control signals, and then this lets you study something interesting. Maybe if we have a new drug that's supposed to reduce instances of Alzheimer's responsiveness, we see all that drug on one side and we say, yes, the drug's working. It's now time to get this past FDA inspection and get it out to market so that people can stop having Alzheimer's, and that would be a wonderful thing to do. So we care about comparing these specific examples to the group as a whole, and we want to do this in terms of a probability process. So where do we go from here? Well, this control chart's interesting, but we need to develop some more advanced math that allows us to compare one particular person to the group, CF my example on height, and we also want to do things that compare small groups of people to the population as a whole, CF, let's say, my class of 17 students to all 200-something plus students that I've taught stats in the last 2 years. And I'm not going further back than 2 years simply because maybe I've changed so much in my teaching process since then, and we've even changed some of the requirements for testing into these statistics courses that you can't compare apples to oranges. So, we want to be able to eventually work towards this idea of comparing people, a single person, to the population, or a group, a sample, to the population. And we want to see how likely is this to occur. We can do that by comparing everything to the normal curve. And when you look at the normal curve, the way I've drawn it last, is I've done it in terms of deviations. And so we have this idea that as we do this in terms of deviations, we hope that we're going to be able to talk about these deviations and come up with something that lets us compare apples to apples. I think that's probably enough for today. So I will see you next time as we continue this discussion, but until then, be safe, study hard. I'll see you around.